In this discussion, we're going to look at how we name compounds and write formulas if we're given the name of the compound. So there are a couple of different types of compounds that we're going to kind of categorize them in as we name them. One would be the binary compounds. These are compounds with only two elements present. The others are compounds containing polyatomic ions. We'll talk about what those are. And then the others would be acids. And those we can recognize in that their formula often begins with hydrogen. We probably in this course will not look at the methods of naming acids right away. I'll probably do that a little bit later in the semester with you. Okay, we're going to break binary compounds down into three types. First, binary ionic compounds. These are going to have metal, non-metal. So the key thing that we're looking for is that you're going to classify the compound because depending on what kind of compound it is, that's going to affect the way that you name it or write formulas from the name. So if it has a metal in it, it's ionic. All right, and if it has two nonmetals in it, then it's molecular or covalently bonded. And then again, if it has a hydrogen in front of it, it's going to be an acid. Okay, this is not in figure 5.1 in your book. This figure is from a different textbook. But if you look at it, it has a nice breakdown of kind of the thought process you need to go through when you're looking at how do I name this compound. So the first thing you want to look at is there a metal in the compound? If not, it's going to be what we're calling a type 3 or a molecular compound. If there is, then we need to look at can that metal form more than one type of ion? If no, it's a type 1, and these are going to be like your group 1, group 2 metals. The type 2s are typically going to be your transition metals. These are the ones you need to be aware that they can form multiple charges, and so there's a little extra thing we have to do when we write their names. So let's start with the type 1s. All right, these have a metal cation and a non-metal anion, and in the formula the metal will be listed first, and also in the compound name the metal will be listed first. Okay, metal cations just get the name of the metal. We don't alter it in any way. However, the non-metal anions, we're going to basically cut off the end and replace it with IDE. So an example, this CaCl2 would be calcium chloride. Okay, we took off the INE of chlorine and replaced it with IDE. Okay, chemical formulas, you're familiar with these already, and they do two things. They identify the elements that are present with the symbols, and then they also tell us the relative number of each atom that is present, and we do this with the subscripts. The subscript will be to the lower right of the element that it applies to. So for example, if we look at this formula for aluminum sulfide, this formula tells us that we have 2 aluminum atoms for every 3 sulfur atoms. Alright, we're going to look at how we show the transfer of electrons with Lewis symbols. Lewis symbols are symbols that are going to show the number of valence electrons present in the particular atom. And the way that you're going to find the number of valence electrons, we've already looked at how you do it if you write the electron configuration. You look for the S and P electrons in the highest energy level. Okay, another easy way to do it is if you go to the row that the element is in, start at the left and count how many S's and how many P electrons do you go through to get to that element, including the one the element is at. that's going to give you the number of valence electrons. So if you pull out a periodic table, if you look at nitrogen, for example, if you start at the left of the second period, you come across, you will count 2 S's and 3 P's to get to nitrogen. So nitrogen has 5 valence electrons. Okay, do the same thing, say, for bromine. If we go to bromine, period 4, we count, we go 2 S's, and then 1, 2, 3, 4, 5 P's to get to bromine. So bromine is going to have 7 valence electrons. So that's how you're going to determine the number of valence electrons. And let's look at what this means. Here we're talking about ionic compounds. So we have a transfer of electrons. So the metal is going to give up its electrons, and the nonmetal is going to accept them. So let's look at, how we would show that. And I'm doing this because I want you to kind of understand when we're writing the formulas for the names, how we get those subscripts. What does that mean? All right, if we look at aluminum, all right, and you should have at this point a cation and anion sheet. All right, if you look on the cation sheet, you will see that aluminum forms a +3 ion. Okay, if you flip that over, you will see that chloride forms a -1 ion. So what does that mean? Well, that means that aluminum likes to give up 3 electrons. That's how it gets to have a full valence shell. Chloride only needs to accept 1 electron to have a full valence shell. So let's look at what our Lewis structures would look like here. Okay, so if I look at aluminum, aluminum's going to have 3 valence electrons, and I'm going to just put them around like that. Okay, chlorine has 7. Okay, so it can, and actually I'm going to use X's for the aluminums just to make them look different. Okay, so then we're going to have 1, okay, one chlorine can accept 1 of aluminum's valence electrons, but aluminum wants to give up 3, so we need basically 2 more chlorines in order for aluminum to be able to give up all of its valence electrons. One will go there, and one will go there. All right. So when we write the formula for aluminum chloride as AlCl3, basically what we're saying is that in order for there to be a transfer of electrons, every electron that's given up is accepted by something. We need 3 chlorines for every 1 aluminum. All right, so that's what we're doing when we're kind of writing the formulas and we're balancing the charges. We're essentially saying that every electron that's given up has to have a place to go. All right, so let's look at what does that mean for aluminum sulfide. Well, we already looked up aluminum. We know it's a +3. If you look up sulfide on the anion side of your sheet, you'll see that it's a -2. Okay, it likes to accept 2 electrons. Well, let's look. Sulfur has 6 valence electrons, and we said aluminum has 3. Again, I'll use X's. Okay, so that sulfur can accept 2 aluminums. All right, so I still got another aluminum, so I need another sulfur. But now that one's just got 1 now. That sulfur needs another one, so I need another aluminum. And one of them's going to go there. And then now I've still got 2 more with the aluminum. And so these 2 right here can go right there. So I need 3 sulfurs to accept the electrons from 2 aluminums. Okay, again, I'm just doing this to kind of clarify for you what we're doing when we write formulas. We are balancing charges, and that's essentially what we're doing. We're ensuring that every electron given up is going to another atom. And so we're looking at, well, how can we combine these so that that happens? Alright, so writing formulas from the names. First, you're going to determine the ions that are present. You can use your ion sheet to do this. In this class, you will always be able to use the ion sheet that I gave you. Then, determine the charges on the cation and the anion, again with the ion sheet, and balance the charges to get the subscripts. That's what I was talking about before. Every electron that's given up has to have a place to go. Okay, so let's look at an example. Here we have magnesium chloride. So we would look up magnesium is +2. Okay, it wants to give up 2 electrons. Chloride is a -1. It only wants to take 1. So in order for that, we need 2 chlorides to balance out 1 magnesium. So the formula for magnesium chloride would be MgCl2. Alright, polyatomic ions. You'll notice on your ion sheet, especially on the anion side, you have groups of atoms bonded together, but yet they have a charge. Okay, these atoms, they are covalently bonded together, but as a whole, they have a net charge. And so they stay together when they go into solution as a unit, but then they are able to carry a charge, for example. They ionically bond with metals. Okay, and we're going to look at these, and you'll find these are pretty easy, the naming process, because they just get their name that's listed on the sheet. So if you had this formula, you would go and look on the sheet to find, well, what is C2H3O2? And if you see that, you will match it up, and it is acetate. So the name of this compound would be aluminum acetate. You don't have to alter the name of the polyatomic ion in any way. Okay, now you'll notice there are some patterns, and I'm just going to go through this quickly, but because we'll come back to this, especially when we start looking at naming acids. But you'll see that there is, for each of these polyatomic ions that have an element and oxygen in them, these are called oxyanions, and they have kind of a pattern to the way that they're named. And you'll have one of them that has an ATE ending. And then if you have that same one, but just one oxygen more, that would be per ATE, so this would be perchlorate. If you take away an oxygen, it's chlorite, okay, ITE ending on that. And then if you take away 2 oxygens, it becomes a hypochlorite. And so you'll see kind of this pattern in several of these oxyanions. Okay, type 2 compounds. These are going to be similar to the type 1, except that now we have metals that can have more than one charge. And so what that means is that when we're naming them, we have to indicate what the charge is on the metal. We have to indicate which metal ion are we talking about. And we do that with a Roman numeral after the metal's name. So for example, if we had FeCl3, all right, iron can be a +2 or a +3. So if I just named it iron chloride, you wouldn't know which one. You wouldn't be able to write the formula because you wouldn't know if it's iron 2 or iron 3. So what we have to do is we look at, in this compound, what is it? Well, we find out, go to your anion, figure out what is my total negative charge. It's a -3 in this case. I have 3 chlorides. Each chloride is a -1. So I have 3 chlorides accepting electrons, which means I need something that's going to give me 3 electrons. And so the iron, since in this formula I only have one of them, that iron has to be the +3 iron. Okay, so you're going to look at the formula as written, look at what is the negative charge, and then see what does that metal have to be, what charge does it have to have in order to fit that formula. And so we would name that iron Roman numeral 3 chloride. Okay, so now you could easily write the formula because you know that this is an iron with a +3 charge combined with a chloride ion. Alright, so let's look at another one. Here, if I have this formula, I know that this is gold sulfide, but gold can have multiple charges, so I don't know which one it is, so let's figure it out. Sulfide is my negative ion, and I have 3 of them, so my total negative charge is negative 6. That means my total positive charge has to be positive 6. I have 2 gold atoms to get that positive 6 from, which means each of them has to be a plus 3. So I would name that, whoops, oh, missed that, didn't I? Let me go back. So I would name that then gold, Roman numeral 3, sulfide. Okay? Now, you will come across an older naming system for type 2s, and I'm just going to mention it here. You may use this as long as you use it correctly, but I put it in here because sometimes in labs or on chemical bottles, you will see this old naming system still used. Basically, in this naming system, it uses the root name for the metal, and it uses suffixes instead of Roman numerals. It's not as detailed, I think, as the Roman numerals, but it's still in use, and so we'll look at it here. Basically, this was established when pretty much we were dealing with metals that only have 2 possible charges. We have one that's higher, one that's lower, and essentially what they did was they just used the IC or IC suffix if it's the higher charge, and the OUS or US suffix if it was the lower charged version. So an example with iron, remember I said it could be a plus 2 or a plus 3. The plus 3 would be ferric. Fer is the Latin root for iron, so ferric chloride, or the iron 2 chloride would be ferrous chloride. Okay, again, you don't need to use these. I would prefer you just stick with the Roman numerals, but I do want you to be aware that these are used. Okay, some common Latin names, then these are for some common metals, are ones that you might see. Alright, so writing names from formulas, let's go back on here. This one, for type 2, they're actually a little easier to do because you actually have the charge given to you in the name of the compound. So the charge on the cation that you're going to use is the Roman numeral, and then you're going to go through the same process. You're going to balance the charges to get the subscripts. Okay, so for example, if I had copper, Roman numeral 1 oxide, the copper is going to be the plus 1 copper, and then the oxide is what it always is, the minus 2. So basically this just saves you from having to look it up on the cation sheet. And so, but this process is still the same. I need 2 coppers that have a plus 1 charge to balance out the 1 oxide. Alright, now, type 3 compounds. These are molecular compounds, and they have 2 nonmetals in them. So, the general format is the same. You're going to name the first element in the formula first, and then you're going to use the full name of that element, similar to the way you did the metals. The second element is going to get the IDE ending. Alright, now, in this one, because these are molecular compounds and they share electrons, we're not forming ions. And so, from the name, if before, to get the formula, we were just balancing charges. Well, there's no charged particles formed in these covalent compounds. And so what we do is we're going to use a prefix in front of each name to indicate how many atoms of each type are in the formula. So actually this is really easy. The biggest mistake I see people make on this is that they try to balance charges when they're dealing with the 2 nonmetals. So that's why the first thing you want to do in looking at naming these compounds is you want to decide, do I have a metal or not? That should always be the first thing that you look at. So here, couple of rules. You're never going to use the prefix mono on the first element. And these are the typical Greek prefixes like what you'll see in your geometry classes. Mono for 1, So for example here, if we have CO2, right, it's carbon dioxide, not monocarbon dioxide. Right, so that's the only exception. Other than that, everything gets the standard prefixes, and these should be listed in your book. All right, now, for type 3 compounds, it's a lot easier to write the name. You just use the prefixes and write the formula exactly the way that the name indicates. So, for example, carbon tetrachloride, 1 carbon, 4 chlorines. Okay, no balancing of charges, nothing. You just write it exactly the way it tells you.